Hello everyone, thank you for viewing my talk. My name's Sam Upton and I'm a PhD student at the University of Southampton, and today I'll be talking about work that I've been doing with my supervisor Adam Pound on covariant and coordinate punctures for second-order gravitational self-force in a highly regular gauge. So this is quite a long title, but I'll guide us through it and explain exactly what I mean with each of these terms. And this is work that feeds into a larger collaboration with other people at Southampton and with people at University College Dublin as well. So, first of all, I'll talk about issues that are encountered in second-order self-force calculations, particularly those that occur near this world line of the small object. I'll move on to discussing the highly regular gauge and how the use of this class of gauges can alleviate some of those issues encountered near the small object's world line. In particular, how the highly regular gauge makes the perturbations less singular, and how that leads to well-defined second-order Einstein field equations. I'll then discuss how the perturbations for the highly regular gauge that we previously found, how one can convert them into covariant form and into a generic coordinate expansion as well. And I'll briefly discuss how one could implement this in a puncture scheme. So I'll give a brief overview of self-force. So gravitational self-force is a perturbative method that casts the presence of the small object as causing perturbations in a background space-time, which describes the supermassive black hole. So here you can see that there's really three main methods for approaching the self-force problem. And here in the lower right, you can see the self-force is really aimed at those of the problem when you have a large mass ratio between the two objects, although more recent work has shown that self-force results could be applicable up to much smaller mass ratios, which is very exciting. So how does self-force work? Well, we have this g-exact, so that's the metric of the full space-time encompassing both the small and the large object, and then that's a perturbative expansion, so we have this G here, which is the metric of the supermassive black hole if it were isolated. So we use either the Schwarzschild or the Kerr metric. And then we have a power series in epsilon, which is the mass ratio. And at each order, we have perturbations, which are sourced by the presence of the small object. Now, the equation of motion for the small object is given as such. So you can see here at leading order, we just have the ordinary geodesic equation, and then we have higher order corrections, which is what we refer to as the gravitational self-force. So the self-force is made up of two parts, a conservative and a dissipative part, and it's in order to correctly track the orbital frequencies for LISA, we need the entirety of the first-order self-force and the dissipative part of the second-order self-force. So it's been known for quite a long time that second-order perturbation theory is crucial for precise parameter extraction from EMRIs. It's not that the first order gives you a lot, gives you something, and second order is a sort of nice refinement of that. As I discussed in the last slide, no, it's really the dissipative part of the second-order self-force is as important as the full first-order self-force. So one of the problems that has been encountered when calculating the self-force is the strong divergences that occur on the small object's world line. So to see this, we split the perturbations into regular and singular pieces. The regular pieces form part of an external effective metric, and they satisfy the vacuum Einstein equations, and the singular field encodes the multipole structure of the small object. So here at first order, it goes like m over r, and at second order, it goes like m squared over r squared. However, we previously showed that in a highly regular gauge, this is less singular. So this previous expression is just in a generic gauge. In a highly regular gauge, this is less singular. If we split up HS2 again into a singular times regular and a singular times singular piece, then we see that the singular times regular piece goes like m times HR1 over r, and the singular times singular piece goes like m squared r to the 0. So this immediately alleviates numerical issues as we have eliminated the most singular part of the perturbation. And also nicely, it allows us to have well-defined second-order field equations, which leads to a well-defined second-order stress energy tensor. So I won't go into the details of how one can derive that exactly, but if you're interested, please send me an email or check out these papers here for more details. So we found the form of the perturbations in the highly regular gauge in Fermi-Walker coordinates in our previous paper. So how will we make them covariant? Well, the method had previously been used by Pound and Miller to create Lorenz gauge covariant punctures from Fermi-Walker coordinate expressions, and we can use exactly the same methods as they used to create covariant expressions in the highly regular gauge. And then one can perform a generic coordinate expansion of the covariant expressions and then decompose into a suitable basis of modes. Then the singular field, we can truncate at some order and distance, and we can use this as input for a puncture scheme, where we use the punctures to solve for the residual field, which then dictates the motion of the small object. So how do we go about converting our Fermi-Walker expressions into covariant form? Well, and all this method is from Pound and Miller. I just want to give a quick overview. So we want to express a point in the field in terms of an arbitrary point in the world line, x prime. So to do that, we first write this in terms of x bar. So x bar is the point where if you were at x bar and you sent out an orthogonal geodesic, you would hit x. And then because we are interested in differences in proper time as well, we then perform an expansion in terms of delta tau to get from x bar to x prime. So how do we go from x to x bar? Well, the Fermi-Walker coordinates are geometrically constructed. So if we look at this picture on the left here, we have our world line gamma. Then at each point, it's labeled by a coordinate t. And then at each point t, we send out orthogonal geodesics, which generate a surface. And on that surface, we have coordinate xi to label each point. So these xi can just be rewritten in terms of a radial unit vector and a radial distance. So because Fermi-Walker coordinates are geometrically constructed, there's a very natural conversion into a tetrad along gamma. So here we convert our point t into the proper time at x bar, so just tau bar, and then x a we can convert using an appropriate projection with the basis with the derivative of Singh's world function. So I won't go into too much detail about Singh's world function, but essentially it's a bitensor here, and Singh with one derivative is a derivative of Singh's world function. So as it's a bitensor, it's a function of both x and x bar, and essentially it gives you half the geodesic distance squared between x and x bar. So when you take a derivative of that, it gives you something proportional to the geodesic distance between the 2 points. Now, to go from x bar to x prime, we just re-expand in a power series in delta tau. After doing so, we can re-express all quantities in terms of powers of a derivative of Singh's world function, and then we can introduce two handy shorthands. So there's this bold R, not to be confused with the Fermi-Walker R that we had previously. This bold R, which gives roughly represents a difference in proper time between the 2 points. And then this quantity rho, which roughly gives the spatial difference between the 2 points. So I can't show all the final expressions for the covariant results here, as they would take up many, many, many pages. But I can provide the leading order for the HS1 piece, so the leading order in distance here. So it should be important to note that each rho and each sigma and each r are a power of distance. So these are both 1 over distance, these expressions. So you can see here that the highly regular gauge has a much more complicated structure just at first order, and unfortunately this continues at higher orders, both in powers of distance and in powers of epsilon. So the process, it's more complicated than the Lorenz gauge. This may be due to the gauge conditions for the highly regular gauge, which enforce the local light cone structure near the small object. This can cause problems when performing the mode decompositions, as any integrals you perform could potentially be more complicated or computationally complex. However, the benefits of the highly regular gauge would far outweigh any issues, we believe, would far outweigh any issues that would occur when performing the mode decomposition. So far, I've checked that some of the appropriate field equations are satisfied. That is HS1 and HSS. Those are both satisfied to the appropriate order. But this lambda here just counts powers of distance. So you can see these are satisfied to the appropriate order. One would need to implement a puncture scheme. In the process of checking HSR, I've done the first two orders. I just need to perform the final check of the highest order. I should note here this HS1, the highly regular gauge, is actually a rest gauge. So this HS1 acceleration appears when you re-expand HS1 along the world line. So to perform a coordinate expansion, which we would need to do if we wanted to implement these covariant expressions we've got, we need to write it in a specific, we then re-expand, or to implement, we would need to write in a specific coordinate system. To do so, we re-expand our covariant quantities in terms of coordinate differences. So, for example, this was previously done by Otterwell and Wardell, and many others have done as well. So we can do this by using various identities, both for Singh's world function and for the parallel propagator. So here, for example, we see that two derivatives of Singh's world function contracted into each other just equal 2 times Singh's world function itself. So we can just perform the various derivatives, contract them, and then check order by order in delta x what the appropriate coefficients should be. And we can do this for the parallel propagator as well. So as an example, this shows that the leading order term of the derivative of Singh's world function is just the negative coordinate difference between the two objects. So it's proportional to the geodesic distance as we expected. So it's proportional to the distance as we expected, the difference between the 2 points. So we end up with a coordinate puncture that's purely written in terms of the metric, delta x, and the fall velocity as well. And then to implement this, we would need to decompose this into a basis of suitable modes. So today I've outlined the benefits of the highly regular gauge and how it leads to a less singular nature of the Einstein field equations. I've demonstrated how one could convert our Fermi-Walker expressions into covariant and coordinate forms using previously derived methods. I'm just performing the final checks that the punctures satisfy the Einstein field equations, and the expressions will be available online and in an upcoming paper. I'm also working on a gauge transformation of existing first-order Lorenz gauge data to the highly regular gauge, so one would have two avenues for coming to the highly regular gauge, either through these punctures or through a gauge transformation. Thank you very much.